Okay, welcome everybody. Today's session is going to be chaired by Rasha. She's going to be the one to lead the session, and we're going to be supporting because we're all supposed to read the book. So once again, I'm Bilikisu Olatunji, and Rasha is going to be the one to take the session. So Rasha, you can go ahead.
Thank you so much, Bukliso. I have benefited so much from this group, so I'm really happy to be leading for this chapter and helping out with the group as much as I can. And so this session will work on chapter 4, and I wrote down some links which maybe I can paste in the chat. That might be helpful. It's a link to the book if you want to be able to follow along, as well as the YouTube channel, which Bilkisu does a really good job for putting all of the previous sessions. So if you missed out on any of the previous sessions before, or you want to review something from the previous sessions, you can find it there. And then also the GitHub page where Bilkisu does a really good job of also putting all of the code in the session. So I'll put this in the chat as well. Let's see if you allow me. You should find those links there. And so today we mentioned we're working through chapter 4, and we are using some of the same packages that have been used in the previous chapters, which is the SF, the Terra package when we get to the raster data, and then also using the tidyverse and the SB data and TMAP for visualizing some of the stuff. So once you get these, have these packages installed, that'll be really helpful. If you need help to install them, there's a section here that you can use as well to install some of these packages if you need that. So this chapter, we are looking at basically how spatial objects can be modified, and in which they can be modified in a multitude of ways based on their location and their shape. We have, we'll be working with different types of spatial relationships. We'll look at two specific ones, intersect and disjoin. And let me put this in visual mode so it's a little bit more easier to see. So we'll be looking at two specific operations or two specific relationships, which are the intersect and disjoin. And then we'll also look at the unique aspect in which spatial objects use distance, and how spatial objects can be related to space, distance, and how those calculations can be used to understand or explore the strengths of that relationship. And then for raster objects, we'll look at subsetting, joining, and aggregating, which we won't cover today, but will be next session. And then just a brief point is that the map algebra covers a range of operations that could modify for raster cells, raster cell values, with or without reference to the surrounding cell values. These 2 points, don't worry about them for right now, because those are relevant for the raster. But for today, we're just focusing on how to do the spatial operations for vector data specifically. And we're going to use the SF package for most of those operations. So the first operation that we're going to be focusing on is the spatial subsetting. And this is the idea that we have spatial objects, and then we want to be able to get subset a particular part of that object and then get new features. So this would be, for example, we have, we want to, all of the countries in the world, for example, we want to subset all of the countries that are within Africa, or all of the countries that are within Asia or North America or South America, etc. So this is the idea. Analogous to attribute subsetting, the SF data frame can be used to, or can be created with a square bracket. We saw this in the previous chapter, where we did also a little bit, I think Tofisa was doing this one, where she demonstrated how to use the bracket operator. So hopefully this will be, for some of you that have been following, this will be maybe a little bit of a review. So we use this syntax where we have X, which is an SF object that the subsetted rows will be returned from. And then we have Y, which is a subsetting object. And then we specify the operation that we want to do, which is st intersect. And we'll talk about more what this particular function does. So the main thing that I want you to understand from this part is that we have, the book shows 3 different ways that we can subset data. And that there's 2 functions that will be all that you really need when you need to subset. These 2 functions are they come from the SF package, and they are intersect and they are disjoint. Intersect is going to be a catch-all. So if you're looking to subset anything that touches, crosses, or falls within an object, you're going to use the intersect. It's going to give you all of those. So say, for example, you have some points and you want to know how many points fall within a particular polygon. You're going to use intersect. It's going to give you all the points that touch, all the points that cross, and all the points that are within that polygon. Okay, the exact opposite of that one is going to be disjoint, this one here. This is going to give you exactly the opposite, which is any point that does not touch, cross, or fall within that polygon. Okay, so the 2 subsetting functions, are the intersect, which is going to be our catch-all to get anything that touches, crosses, or within the polygon. And we have disjoint, which is going to be anything that does not touch, does not cross, and is not within that object. And then, as I mentioned briefly, is that the book shows 3 different ways that we can subset. One is using the bracket operator, which we'll do an example of. And then the second way is to use kind of like a logical intermediary. We'll talk about it, even though it's not maybe something you really need to do. You can choose one of these, number 1 or number 3, which are way more easier and sort of straightforward. But if you are a person who's pragmatic and you want to kind of see the steps that you're working through, this can be maybe something that you work through as well. So first way is to subset, use a bracket. We use a logical intermediary. The second way, third way is we use the from the SF package, we use the ST filter, which some of you might be familiar with if you're familiar with using the tidy way of coding. So we'll talk about the first one using the bracket. So how this will work is you have some points. You will put that object there. And then inside the bracket, you will put the polygon. And then you will leave this argument open, which is the one that's between the 2 commas. Also, if there's a question, please let me know. My screen is full, so I'm not maybe able to see if anybody have a comment or something like that. So coming back to this, we have an argument that's open here, where we don't specify anything, and I'll touch on that as well. And then we specify the argument that we want. We want the intersect, all the points that touch, cross, or within. We specify that here. We want the function that's disjoint, anything that does not cross, touch, or is within, we specify that here. Okay, so that's the first way that we can subset data, and we'll look at an example of this as well. The second way is using a logical intermediary. And basically what you do is you use the function intersects, you specify the points, you specify the polygon, and you save this to, or you assign this to an object where you have all of your intersecting points. And just a small disclaimer, I code a little bit different. I use the assign operator at the end rather than at the beginning. For me, it just makes sense logically, like I'm doing all of the steps and then I'm assigning at the end. So I hope this is not a bother to anyone, or maybe it's something that might be useful for you in your coding. So coming back to this, we have the function st intersect. We specify all the points. And we want to know which of those points fall within this polygon. And then we save that to an object called intersecting points. And then afterwards, we grab all of the intersecting points that are greater than 0. So essentially what this step here does is it tells you, okay, these are all of the points that you have. And within these points, it's either it's a logical value, either yes, it falls in, or no, it falls in, it does not fall in. So in this step, you filter out all the ones that fall in. Okay, and then you save it to an object, and then afterwards you use the bracket operator, which we talked about in the first step. So you specify your points and you put all of the logical outcomes here, or all the points that are true do fall in. So it seems like kind of a longer way to do it. So that's why I say like recommend maybe like doing number 1 or number 2, or sorry, or number 3. If you want to subset the data. Third way is to use the SF ST filter, and then you specify a predicate, which is going to be your subsetting function, which one you want to use. Okay, so how to use this, you're going to take your points and then you're going to pass them through the filter function, and then you're going to say all of these points I want to know, filter all the ones that fall in this polygon, and then you're going to give it the predicate or the operator, and you're going to say all the ones that intersect. And keep in mind, you can change this. You can use the disjoint, or you can use anything, any of the other functions that we specified. So I will take a pause here really quick. Is there any questions or anything maybe that was confusing so far?
I'm actually watching the chat box. So, but I've placed in the chat that if you have a question, you can push it in here, or you raise your hands, then you can kind of speak during the session. So I think that, so if there's any question, you're free to ask at this point. So questions, comments, or addition? I think we can go on for now.
Okay, perfect. Yep. And if anything comes along, just please so let me know as
Yeah,
well.
definitely.
Okay.
Thank you.
Oh, thank you. Okay, so we talked about 3 ways that we can subset. We're going to look at maybe a sort of a real world problem where we have a data set that we get from a part of the SP data package. And it's looking at the New Zealand. We have some regions. I'm just gonna use the word polygon. It might be maybe more easier. So we have some polygons and we also have some points. And just always, I like to kind of be familiar with the data. So this particular data set, I like to also look up the documentation just to make us more familiar with it. And in case it comes back again, we can be able to recognize what was inside that data set, or maybe we can use it to even like come up with questions or look at maybe a particular problem together. So in the NZ data set, I'm going to look up documentation by putting the question mark there. And then, so basically this data set, we have a few columns in there. We have a name, island, area, population, medium income, and also about gender, the ratio, and also we have that column at the end that is the geometry. And if we take a look at this NZ, let me make sure I've loaded all of my packages first, which is an important thing to do. And then I'm gonna come back here where we were. And then I wanna just take a look at this. So the NZ, as we see, it have all of these columns, which are the 16 regions. So we have 16 polygons. And these are the names. And then this column specifies if it's a north or south island. And then the land area. So we see like Canterbury looks like the largest one. We have population, and looks like this Auckland is like more populated. We also see by income. We also see by like gender ratio. Maybe we just have an idea like this one have more male to female ratio. And then that column that gives us the geometry of how to draw exactly that particular polygon or region. So that's the NZ where we have our polygons. And then I also just pulled up the NZ heights, which are the points within New Zealand as well. And just for quick good practice to look up the documentation. So the documentation for this data set, we have 101 top highest points in New Zealand as of 2017. And each point have an ID, which is this column. And then it also has elevation and looks like it's in height above sea level in meters. And then it has a geometry, which specifies for us as a point here. Okay, so if you remember also that we said in the beginning of this, we always want to double check 2 things that if you want to compare 2 things or do an spatial operation between 2 objects, Number one is to make sure they're both geographic objects. You cannot have like, in certain cases, but for today, we want to make sure that they're spatial objects. They're both geographic objects or spatial objects, excuse me. And like, for example, you cannot have like a table and you're trying to join it maybe, or trying to subset it, maybe something like that from a SF object. So we need to make sure they're both spatial objects, number one, and number two, that they both have the same coordinate reference system. There's many ways to kind of check this, and it's covered in more later chapters, but for today, we just look at, for example, the class, and we see, okay, the NZ, which is, remember our polygons, they are in SF, which is good. They're both spatial, this is a spatial object. And the NZ heights, which are the points, the highest points, this is also an SF. So that's amazing. They both are spatial objects. And then we want to check that they're both in the same coordinate reference system, which is a way of like making it so that you're comparing two things that are in the same plane level field, okay? You don't want to have something in another coordinate reference, something that was measured in meters and compared to something that's measured in feet, something like that. You want to make sure that it's in the same coordinate reference system. So we're going to check it. Although this is kind of hard to read, if you can also see the coordinate reference system here when you just put the object name, and then the output it will show you here. It will tell you, okay, this is simple feature collection, again, SF. And then it will tell you also the geometric type. And then also tell you that this is the projected coordinate reference system, which is using this one, NZ GD 2000, or the New Zealand Transverse Mercator 2000. Okay. And then if you do the same thing for the heights, we see also it's in the same coordinate reference system. And we can double check this just in case that they're both using the same coordinate reference system by putting two equals together, and we should get it true. So we're good. We checked off the two things. They're both spatial objects and they're both on the same coordinate reference system. We can be able to do some operations with them. Okay. So we're gonna look at the first way. Remember, our goal is that we wanna we want to be able to look at, we have these 16 polygons and we have 101 points in New Zealand, and we want to look at a particular polygon, which is the Canterbury polygon, and we want to know how many of those highest points fall in that one. Okay, so I'm going to show it based on the two ways of subsetting, the three ways of subsetting that the book discusses. So this is the first way. We take the New Zealand, which is that 16 regions, the polygons, and then we filter for Canterbury because you want only that one. We want only this polygon, and then we want to know how many points fall within it. So we're going to filter, and then we're going to save it to an object or assign it to an object called Canterbury. So we'll go ahead and run that. And then we're going to use our bracket operator that we talked about. And then remember how we use it. If I go up here just a little bit, we put the points, we put the polygon, we leave this argument blank, and then we specify the operator. We want intersect or we want disjoint. Okay, intersect is all the points, remember, that touch, cross, or are within. And disjoint is exactly the opposite. So let's come back here. So we put our points, NZ heights, those 101 points. And then we specify the polygon specifically because we filtered for it for Canterbury. So we put that here, and then we leave the argument blank. Okay, and then we can save that to points in Canterbury. Okay, I just want to show that basically these two here are the same thing. And you notice here, I didn't specify, like I didn't put the OP, you know, the operator equals ST intersect. I just put, I just left it open. I didn't specify all of this, but it will still return for me the correct option. Why? Because if you don't put anything, R understands it as default. You mean this operator, you mean the intersect, unless you specify specifically, I want the disjoint. Okay, so these two here are the same exact thing. Okay, Here I didn't specify the operator. Here I explicitly write the operator, I want the intersect. So anything that touches, crosses, or is within this polygon, any points that are within this polygon. This is the opposite just for demonstrating it, but we don't need to worry for that one right now because our goal is to find how many are within, not outside. So we can maybe get a feel or visualize what we just did. So I'm going to be using TMAP here. So these are the 16 regions of New Zealand. And here we have all of the points, the 101 high points. And then here I'm also specifying, if you're familiar with the TMAP, you put the polygon or with the spatial object that you have, and then you put if you want a polygon or a symbol to fill it in. So, and then here I just added that, I put them basically together. So this is going to show us all of the polygons. This is going to show us all of the points. Okay. And then this is going to give us a title so we can understand what's going on in the title. And then this is just setting the background as blue. So I made a series here that we can look at. And then here, this is arranging all of the points or all of the graphs that we made together. So let's pull this out so we can look at it more bigger. Okay, so these are all of the points, and we can check if what we did worked. So these are all of the points that are within Canterbury, and Canterbury is the region that falls here in the gray. And then this we used the intersect function. Using the t-intersect that we specified in the bracket operator. And it looks like it filtered all of the points that fall within. There's other points that fall in other regions here, but they're not there. And then here, this is when we use the disjoint. So we show these are all the points that fall outside of Canterbury. So all the points that are not within here are selected. Okay. Let me take a quick pause to make sure if there's anything that might be confusing or anything that I can look back again. Any questions or anything that was maybe need more clarification?
I believe you're doing it so far. You're really doing great. There's no question yet. No question. Do you have any comment? The observations? Any comment? Questions? Okay. So I think we're still good to go.
Okay.
Yeah.
Sounds good. If there's anything else, as always, let me know. So
Okay.
coming back.
Okay. From
To
Livia,
this one.
everything is okay, and thank you.
Awesome.
So thank you, Livia.
Awesome. Thank you so much. And if you think of anything else, just also let me know. So this here just saying that basically you want to make sure that, again, like both objects, they are both of class SF or SFC. And then we double check that both of them are in the same, they're both geographic objects. Let's see. And then just remember that the ST intersect is a catch-all for anything. So let's do maybe a quick test or quick pop quiz. So if I want to have all of the NZ heights that fall within Canterbury, and I want to do a disjoint, how would I write this code? So we have to fill in the missing here in both of this. So in the disjoint, what is missing? let's go over that one maybe first. What is missing? How can I fix this to be right? And I can get all the points that don't fall in Canterbury. You can put in the chat, or you can, so you can let me know as well. If anyone like raised their hand or something.
Okay, we have somebody just joining us now. Okay, Lawa, you're welcome.
Thank you.
So you can put your answers in the chat. Okay, maybe I should try.
Give it a try.
Okay. Um, that would be I think the third option that I'll go with now. Would this be okay? I don't know.
Did you put in the chat? I can look, or
Yeah, in the chat.
okay, let me have a look.
Oh, okay. Yeah. Is that okay? Is
I'm gonna put it here so we all look at it.
okay.
This is
That
yes.
so
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 so you put here, you did correct. You put the points, and you put within there all the ones that you want to get out of the polygon, and you specified you're just missing one small thing, that this argument here in the middle is open, which is still gonna I think it's still gonna be correct, and we'll try it. And then you specified the operation, you put st disjoint, which is perfect. So we'll give it a try. And it did it correct. It worked out perfectly. So nice job.
okay.
Yep.
Thank you.
Yes. Yep.
I think that's the third option that you showed up there.
The
The
third,
shortcut yeah. Instead of
yes.
using the long method,
Yep. The second option is too long. Like it's not too long, but it's just there's a lot of like intermediary steps
Mm-hmm,
that
mm-hmm.
you can do, you can filter out. But this is just very kind of straightforward. You put the points, the
Okay, for the
polygons, and you
first,
specify the operator,
yeah.
which you did perfectly. Nice job. I
Thank
love
you.
it. Yep.
Mhm.
And we head back here. We're here. So this one, I think we need to go down one more under the engage. Okay, so then what about this one? If we want to actually do the opposite of the disjoint, how can we make this line correct?
Think someone should give it a try here.
Give it a try.
Mm.
It's okay to be wrong. We're all like learning too. We're looking at this line here. And I see an answer from Victor. Yes, we use the ST intersect. That's correct. I'm gonna copy what you wrote. Can you specify where we add it? You're correct, we use this function. But where we add it?
This you add it as an argument to OP, the OP parameter.
So you mean like this?
Yes, like that.
Okay, perfect. And that's also correct. Nice job. I'm glad we're working together. So
Thank
nice job,
you.
okay, so nice job, Victor. Yes, excellent. That is amazing. Okay, so we're gonna go to something. We're gonna go to another question. Okay, so we looked at the I think it was here. We looked at Canterbury, which was in the gray, and we were able to subset all of the points that fall within there. Now the question is, how many of those points fall within the Canterbury region? How can we do that? How can we know how many fall in there? We subset it, right? We filtered subsetted all the points.
You get the number of rows from the data. Frame.
Something here. I didn't. I'm missing an S there.
Is there a function that
this object
will help us do that?
Say one more time.
Is there a function that is going to do that, or can we use the regular R conscious of counting the number of rows within the data frame?
You're asking, is there a process of being able to like use the number of rows?
Great. The question.
After filtering, if we just count the number of rows.
Yes. Yep. So after we have filtered, we can count the number of rows. That's exactly right. So if we did, for example, say after we have, this is kind of just the same steps we did in the previous sections. So we saved as that region Canterbury. We put the points here, points, and then this is the polygon. And then if we don't specify or specify, it's still going to use the ST intersect. Okay, so this is all the points. And then exactly as you said, Victor, we do n row. And then we can get, these are how many of those 100 points fall within Canterbury, which is the largest region in New Zealand. It's exactly right. Perfect. Nice job. Good job, guys. Maybe I don't need to be here next time. So far, we've been using the function like this within the bracket. Either we leave it blank and maybe we specify the operator, etc. But why we leave this like that? What's the purpose of leaving it open in that particular argument? So here, this is just kind of showing in this block that when we leave this open, let's just kind of run through it. So when we specify 1 in there, it returns like the first column back in your data set. And then here, this returns the second column. This then returns the third one, which is a geometry. So just to show, and then if we do this one without specifying a number or just leaving it blank, this is going to bring all of the fields back. Remember with me that the NZ heights, this is what it looks like, that data set. So if you specify 1 in that subsetting, it's going to bring the first column only. If you specify 2, it's going to bring the second column. If you specify 3, it's going to bring the third column. If you don't put anything, it's going to bring back all of the columns. So just to kind of show what happens here by bringing up all of the column names. And in case you maybe don't need all the columns, you have a lot of data set, you just need the first column or the second, for example. Okay, now we go to the second way that the book shows to subset a data set. Remember, this is kind of the little bit longer way of subsetting, but I'll explain it just for purpose of like just being here, but we don't necessarily need to use this one. So again, just for refresh, this is using the st-intersect. We specify the points, specify the polygons, we save it to an object or assign it to intersecting points. And then we grab all of the points that are like basically true or they're greater than 0. We save it to a logical outcome. And then out of those points, we use the bracket operator. And then we put out of those ones that fall in, bring those back for us. So this is kind of just a way to show it. So st-intersect, we specify the points here, polygons here. We save it to intersecting points. So let's run that really quick. We grab the class, and it brings it back as this SGBP, which the book explained, but I don't remember what it was. Something like, sorry, right here, sparse geometry binary predicate, which is a list of lengths of X in the spatial operations. And then afterwards, we convert it to a logical outcome. So just so we can see together. It's going to tell us if it falls, the point falls in there or no. And then by specifying anything greater than 0, it gives you everything that is true. Okay. And then here, this is something we're familiar with because we used it in the previous step. So if we run that and we do this, and we can check too to make sure the n rows, as Victor mentioned earlier, we can pass it through here. We should get 7. So 70 of those points fall in Canterbury. Okay, so that's the second way to do it. It's just more intermediary steps. And then the book also kind of tries to explain as well this idea of having, like, I'm trying to understand or trying to explain what the sparse geometry binary predicate. And yeah, so I think it's maybe not helpful in this case, but we'll go to the third option or the third way to be able to filter, which is also straightforward as number 1. So you take your points, you pass them on to ST filter, and you say, I want all the points in this polygon. And then you specify your function, st-intersect, okay? And then, okay, so we can take a look at this. We take all of our NZ heights, the points, filter within Canterbury, because we specified it up above. And then we put the predicate or the operator or the operation is in st-intersect. Okay, and then this is another way of subsetting. So you're taking the heights. I believe this was trying to show us like this is trying to show us like that, like all of the ways that we subsetted are the same or they're identical. So you can trust me, all of those ways work. They're all true. So all of the ways that we did, whether it's the bracket or the logical way or the logical outcome intermediary or the way of using this way, using the ST filter is going to give you the same thing. Okay, so here we save that object to Canterbury height 3, and we can compare it to any of the other ways that we did, and it's all going to be true. Okay, so that's everything you need to know about subsetting. Okay, there's 3 ways to do it. Highly recommend number 1 or 2, whichever one maybe is more easier. Let me just go back up, sorry for your eyes. So there's 3 ways to subset: using the bracket or using the filter, where you specify just directly and more straightforward the function that you want. They'll all give you the same thing. Okay, so that's everything about subsetting. We go into now this section about topological relationships. So this is trying to describe the spatial relationship between 2 objects. Okay, the book talks about binary topological relationships, which are logical statements. binary always means true or false, like, or it's like binary, 1 or 2, between two objects. So this can mean something like, does object 1 equal object 2? Does object 1 intersect object 2? Does object 1 cross object 2, etc.? Or is object 1 contained within object 2, etc.? And then also the book introduces this idea of the DE9IM string, which we'll also go over. Why is this important? Let's go back, let's go to here. This is the figure that's in the chapter. And then it's showing you the different functions that you can use to look at now two objects and how you can compare it. You can use ST-intersect or ST-touches to see if the object, for example, the one that's it's kind of like a salmon color, this one here in the top, and then the purple one on the bottom here, how they interact. So you can use these functions, and it will give you the if they do intersect or if they do touch, for example. You can also use the overlap. It can tell you, for example, this salmon one overlaps here with the purple one. And then for the DE9IM string, just we're gonna go over it in the next section, so don't worry for this one. So these are just all the different functions in the SF package that you can use to be able to explore different kinds of relationship, like, is this object the bigger one inside, or is the smaller one contained within the other one, etc. And then remember the disjoint. If it's completely outside, it's not touching, it's not crossing, it's not intersecting. Let's keep going down a little bit. Okay, so we have this example now generated by this code. We have some points and we have a polygon too. And then we want to be able to, we can use the same function again to explore the relationship between those points and the polygon as a second object using intersect. Let's see. Okay. I want to come down to the example that we have here. I need to run the previous ones and transfer. Okay, so the next thing that I want to talk about is this. Maybe I will cover. I think I will cover this one first, this DE9IM, and then come back to the distance really quick. So because it was shown up above, so what it stands for is dimensionally extended 9 intersection model, and the idea is that it creates a string that allows you to understand what is the relationship between these two objects, and all of the things that encompass those. And let's see. The basic idea is that, I think it's probably maybe better to show you. So let me run this code here from the book. Okay, so we have these two objects, okay, or these two polygons. We have X and we have Y. X is this one here that's in the blue, and then Y is the one that's in the yellow, okay? And when we say like interior, we mean like the inside of that. So anything that is contained in X, we count that as the interior, okay? Anything that is the boundary, so anything all the way around it, anything that's around it, we call that's the boundary. And anything that's outside of that completely is the exterior, okay? So if we're looking at X, which is the blue, or the top here. Its interior, how does its interior compare to y? Is going to be this area that's shared here in the red. Okay, so that's the relationship between the blue, the x, and the y. What's shared with them, as far as their, or what's y, how does it cross inside the interior of x? Yes, and it's shared in this red area. And then with the object, with the comparing the two, it's a little bit kind of complicated, but to break it down, so we look at x again, and we look at its boundary. So that's anything around it. Is there anything that touches or is within for y? Yes. And it's going to be this region here. This boundary is shared between x and y. Okay. If you look at, for example, the exterior of x, which again, remember, it's this object that's outlined like this in the blue. Anything that is outside of it completely is this area in the red. And where it shares, where x and y share, each share together an exterior, is within this area here that's red. So the idea is that we make kind of like, anytime that we're using those functions like st-intersect or st-disjoint that we used earlier, in the background, what R is doing is that it's actually creating a matrix. It's looking at, for example, does object X, its interior, does it overlap in the other object, for example, and does it intersect at a line? Does it intersect at an area, or does it intersect at a, or doesn't have no intersection at all? Okay, and it creates matrices based on that. So for example, if we look at the interior of X again and Y, there's a shared area. So what we do is that would be coded as 2. Okay, and then if we're looking at, for example, let me see if I can pull this out. I can be able to scroll down to the next section together. Okay, so it fills out a matrices for each of these based on the interaction. So for example, the interior of X again, and the interior of Y, which is the yellow, yes, it's shared and it's an area. So if it's an area, you put 2 in the matrices. The interior of X and the boundary of Y. So this is the second one here. The interior, so anything inside of X, the blue, and the boundary of Y. So the boundary of Y is like this, and they're shared, it's a line. So we put 1. And then, for example, this one, the boundary of X, which is everything around it, and the interior of Y is shared by a line, so we put 1. Okay. So that's the same idea. That's the idea of the DE 9IM string. And then once you have this matrix, it's flattened. So all of these ones here, like 2, 1, 0, 1, 1, 0, etc., it's flattened down just by row wise. And then for all of the zeros, we just put an F, and then that's what we call as the string, the DE9IM string. And in the background, it uses that. So for example, anytime you put in the code, you say like an st-intersect, it's going to look at what's the DEIM string, and it's going to return back either like a false or yes, or it's going to subset for you, for example. It's a little bit complex, but is that kind of helpful? It's just kind of to show you what happens when you put in those functions into R, to understand how they relate together. I'll take a pause here, see if that was kind of helpful, or if there was any questions.
Let me use this opportunity to thank Hassan. Thank you for your presence, and we're glad that you find it interesting. So we'll have the recordings on our YouTube channel, and we're going to share it with all of you. Okay, thank you, Victor, as well. Thank you. So we'll share the recordings on the net, on our LinkedIn, the WhatsApp group, and share as well through the Meetup page. We'll get it across to all of you. Thank you. Yeah, thank you so
as well.
much. So we'll continue there.
Okay, sounds good. Thank you as well. I'll extend a thank you with you as well. So we went over the DE9IM strings, okay? It's kind of, again, just the main idea to understand here. You never have to probably calculate this or figure out what the string is, but in the background, R does this to be able to help you to understand how two objects relate, if they fall, or if its interior is related to, or it falls in. It uses that string in the background, and then it returns back to you if it is true or false. And then as a result, you can subset, you can do different types of operations. That's just a small thing to understand of what's happening. I'll come back to distance relationships. So here we have, topological relations presented in the previous sections, they're either binary, so it means that the feature is either intersecting or it does not. And what's important to know is that distance is continuous. So the distance of two SF objects, they can be calculated with ST distance, that function, and which is also behind the scenes is basically doing distance-based joins. So in this code here, we're going to look at the distance between the highest point and the centroid of the Canterbury region. Okay, so here we are going to run this. So we have the points, and here we are picking let me run it this way so we can all see together. It's picking the highest point, and it's going to order all of the elevation points and then pick the highest one. Okay. And then here we're using the ST centroid to find the centroid of Canterbury. Okay, and here we use the function ST distance, and we put in that point that we found on the centroid of the region, and then we calculate. It's going to give us the distance, and it's really nice. It shows you here. This is the distance in meters. So the distance between the highest point and the centroid of Canterbury. So that's one way you can explore like distance relationships. Another way here is this is using the, let me run it for example. This is filtering out NZ and looking at anything that have Cantor or another one here called Otago. This is kind of what this means. So it's either have Cantor or Otago in the name, and we save it here. Okay, so it's going to filter out those two regions. And then here we are taking the first three columns. This is just showing you different ways that you can use this ST distance. So maybe we want to see like the first three columns and the distance between those first three rows. I'm sorry, first three rows of the points and how they relate to the either the Canterbury or the OTAG, and it's going to give you the elevation distances that is different between them. Okay, so that's what is showing you here. The other thing to note is that here, like we saw some zeros. So this is saying that the distance between the second and the third features, those the difference between them is 0. And it's letting us know that, for example, the distance between points and polygons refer to any distance in any part of the polygon. And the second and third points in the NZ heights are in Otago, which can be verified by the results below, not showing. So just the idea is that you can use this function to calculate any distance, any distances that you want to look at. Okay, this is just showing us, like, for example, different points and calculating them to different polygons. For example, we went over the DE9IM, which is again just what R does in the background. It calculates a string, and then from that string, it's able to return to you what is happening with the relationship between two objects. The second thing, and I also want to ask how I'm doing on time as well, Professor.
Okay, well, we can still go until 6:30. Like, okay, so we still have like 24 minutes.
Okay.
Yeah.
Okay, perfect. Okay. I think I can cover like maybe this one, spatial joining and distance-based. Maybe the aggregation. Well, I'll try my best.
Okay. Yeah, no
so
problem. We can always extend it to the next session.
yes, we can
Yeah.
always bring it to next session.
So that
Okay.
yeah, it's okay. Let's just see what we can cover. It's still a book. We can't finish the whole book in one day.
That's true.
Okay.
Okay,
Thank you.
sounds good. Thank you. Thank you as well. So this one here is still related to the DE9IM string pattern. It's just showing you, like, and this will be something maybe that's covered later, looking at queen and rook relationship. So I think that there was let me just run this first because it might be easier to show. I think access here, perfect. Okay, so just for visual, this is kind of the same thing as in chess. So the queen can be able to move in all of these directions. The rook can only move diagonal. Okay. And the point of this is that from that DE9IM string that we can specify something has a queen relationship. And this will actually be very important, especially when we get into more complex like spatial analyses. You'll want to look at how polygons that are maybe next to they have a queen relationship, like maybe they're connected by all directions, or maybe they're only at a diagonal, for example. So this also is kind of just keep in the back of your mind, is that it uses again this DE9IM string, and if it's in this pattern, it determines that it's a queen relationship, and it uses that later on to when you're using like spatial analyses, you can specify the kind of relationship that you want to use between different kinds of polygons. So just the way that it, just for fun, the way that it determines this in the background R is that it looks for the fifth position in that DE9IM string, and it looks for a true. Indicates that these two polygons, they don't have an non-empty intersection, which could be a line or a point. Okay, so those two polygons are considered queens of each other. And then in the opposite, in that fifth position, it looks for a 1, and then that determines if two polygons intersect exactly at one dimension or at a line. And then this condition is needed for the polygons to be considered rooks of each other. And then this is just to generate here. I'll cover also spatial joining. So far we talked about subsetting. We talked about the using distances. And then we talked about how if two things can be related. And then now we can discuss for the spatial joining. So say that you want to join two objects. They have to have a shared key variable together. Okay. And as with like attribute data, joining adds a new column to the target object. The argument X is going to be, the argument X is in joining the functions from the source Y. Okay. So here, this is kind of giving us example. Imagine that you have 10 points randomly distributed across the Earth's surface, and you ask for the points that are on land and which countries they're in. Implementing this idea, and they give a small reference if you want to look at this as well, for building your geographic data handling skills. And then so the starting point is to create points that are randomly scattered over the Earth. So they're gonna just create 10 random points that are generated across the earth. And here, I think this code goes, this code is showing the world random. So those are, allow me 1 minute, the random points. So the code above, it generated just 10 random points. If you want to maybe switch it or mess around like with it a little bit, you can. But basically this code just generates 10 random points across the world, which are here. And then we are gonna subset from the world those random points and save it to an object called world random. And then we're gonna find out if they actually fall, because remember this is subsetting still. We are subsetting which ones fall within an actual country. So within those 10 random ones, the ones that actually fall on land are these 4, and they happen to fall in Mexico, Poland, Paraguay, and Morocco. And then here we just visualize this. So out of the 10 points, 4 of them actually land on a country. Here we are looking at, so those are the 10 points. See, some of them fall like in the sea, some of them fall, let me see if I can run that again. It just disappeared. This is the one we just ran. So those are those 10 points that we talked about. You can count them, just 10 here. And then 4 are the ones that, I think I ran it twice, maybe. Yeah, so they should still be those countries. Yeah, that's correct. Okay, so the countries you said, Mexico, I think Paraguay, Morocco, I can't remember the 4th one, but so it's gonna pick for us, or basically we're visualizing those here. But just the idea is that we use this to also do a somewhat of a spatial join, or to subset, so we can be able to do a join. And for the join, we're using st join, and we have those points, which are going to be 10, just to familiarize ourselves with it again. And then from the dataset world, I think we have used this dataset in the previous chapter, so you guys should be familiar with it. But just in case you are not, let's take a look at it really quick. So this data set, it has all of the countries in the world, and then it has like just different columns, so specifying the name, the continent, the region, some population and area, and then some other like demographic, like life expectancy and GDP. And then, so here what we're doing with that join, we're specifying the points, and then we're specifying the where they fall within the world. And then we just specify this column name long, which has the name longer for the country. And then here we are just going to visualize the randomly joined points. Okay, so that's an example of doing a spatial join. And also the red is highlighting just, or the soft kind of thing there is highlighting where they fall within an actual land or a place in the world out of the 10 points. So just for, by default, the SC join, it performs a left join. So meaning that the result of an object contains all of what came from X, including the rows, but no matches in Y. So just important to keep that in mind. I think this was also covered previously by Belfiso. But the ST join can also do inner joins. And the way you can do this by setting an argument left equals false. Okay, so just like here, we can set an argument left equals false, and that's if we want to do inner join. for between the data sets. We'll take a quick pause there. To see if there's any questions or anything was maybe not clear for the spatial joining. Most of these functions, they're coming in from SF. So I like that they're like all ST intersect, ST disjoint, ST join. So they're very clear, very easy like to find.
And to remember.
Yep.
So okay, this almost 6:30. I think maybe well, if there are questions, please put them in the chat or just signify if you have any question. So maybe because I still look at the book, we still have a lot to cover from the distance-based joins. So why don't we do that in the next session? So
I think
that
we can
it will be
cover that in the
easier
next
for. So that's it. So if you have any questions about what we've done so far, so that the next session we'll be looking at the distance join, the spatial aggregation, then also we still have the joining in congruent layers, the special operations on raster is a lot. So I think it will be better we round this recording here. So I don't think there's any question now. So I think we'll
I think that's a good idea because there
stop
was a
it
lot
here.
covered already.
Yeah, it's
that's
a
good
lot.
idea.
It's a lot.
We can
A
start.
lot of terminologies here and a lot to grasp. That's just it because I was just looking at the book. I don't think we'll cover everything today. So I think this is what we'll call it a day. I think you'll be okay with that, Russia?
That's totally fine. Yes.
Yeah. So we'll look for a date for next session that we'll be able to round that up. So the date will be shared with everybody on Meetup, and we'll look forward to that date. So thank you so much, Rasha. You really take a lot of load off me, and I think you did a great job. You're a natural teacher. You engaging us was really awesome, and I think a lot of people benefited from that. Thank you. So thank you, Victor and Livia, Hassan, Laura, Insika, everybody that joined today. We're grateful and we're really, really appreciative of your interaction as well. So I think it made Russia more comfortable first time. I think that makes you a lot more comfortable. So the next session will have more fun. So thank you so much once again. I believe we'll see you the next session then. So thank you,
Sounds great.
everybody.
Thank you as well. Thank you.
Thank you. So I'll stop the recording here.